Hello everyone, I just finished participating in today's Codeforces round, and I'm gonna be trying to explain my solutions. I managed to solve A through D1. So let's get into A. In problem A, we were given a binary string of length n, and we had to modify this string such that for every substring, contiguous substring, of length 2 or more, the number of ones in that substring is greater than or equal to the number of zeros in that substring. That's basically what we had to do. Let's see, if there are two zeros next to each other, we know that we have to put two ones between them. That's because if we select any two or three of these, then if we only put one between them, it won't be sufficient, because if we select these three, there will be more zeros than ones. And if we put two ones between each zero, then we see that it is sufficient, because we can select any substring of this and there will be more ones than zeros. If we put more of these together, so it's 0, 1, 1, 0, 1, 1, 0, we can see that the condition still holds. Basically, we go over the original string, calculate the number of ones between each pair of zeros, and if it's less than 2, then we add that much to the answer. So I can show my solution. I just go over the numbers in the string, and I count how many ones there were between each pair of zeros. If the number of ones, this count, is less than 2, then we add the difference to the answer and then print out the answer. In B, we had to calculate the number of permutations such that this equation holds a number of permutations of length n. What I first did is try to examine what this equation really means. So let's have some permutation. Let's see what this the greatest common divisor of this sequence can be. If the permutation is, or if n is even, then we can have 1, 2, 3, 4, for example. Then what we can do is pair up the odd numbers with the even numbers. So for 1 and 3, we had to put one of 2 or 4, so we can do 4, 1, 2, 3. These multiplied together will all be even, so the greatest common divisor will be bigger than or equal to 2, which is bigger than 1. The next part is realizing that the greatest common divisor cannot be anything other than 2, because let's try to say that it's 3, for example. We know that for each of these products, pi times I, we know that either pi or I has to be divisible by 3 for the greatest common divisor of this sequence to be 3. Well, we know that a third of i's, so a third of the numbers from 1 to n will be divisible by 3. So that's n over 3. And the third of the permutation will be divisible by 3, so that's another n over 3. Which means that we can have 2n over 3 numbers in this sequence be divisible by 3. Which basically means we can never have all the numbers in this sequence be divisible by 3. And we can generalize this to k, saying n over k plus n over k equals 2n over k numbers will be at most divisible by k. And we see that this will only be bigger than or equal to n if k equals 2. And when k equals to 2, we also have to check whether n is even, because if n is odd, then we can't solve this. We can't solve the problems, and let's do it on an example. 1, 2, 3. We can put 2 here, and then 1 here, and we're gonna be left with one odd number. In the problem, we had to calculate how many of these there were. So what I did is just I just checked if it's even. If it's even, then we're gonna do n over 2 factorial squared. That works because we can put the even numbers in the place of the odd positions, n over n divided by 2 factorial times, and we can put the odd numbers in the even positions, n over 2 factorial times. Otherwise it's 0, because we just pre-calculate the factorials and then print this out. I take modulo. Problem C was a bit more tricky. I'm not sure if why I don't have like conclusive proof of why my solution works, but it seemed to have got accepted, so I'm pretty sure it's correct. Basically, in this problem, we are given, well, not given, we have like a hidden permutation, and we have some data about, so the data that we're given is something to do with all cyclic shifts of this permutation. For all cyclic shifts, which is described here, it basically means taking the last I elements and putting them to the beginning. We know what the power of that permutation is, and basically the power, it looks something like this. Let's do some permutation. 2, 1, 5, 3, 4, 6, and we can sort of look at the power if we were watching this permutation from like this wall, from all places in the wall at the same time. We're watching the permutation, or we turn on a light that comes from this wall. And let's say we have towers, so the first tower is of size 2, then 1, then 5. Next tower is of size 5, then 3, 4, and 6. And we are given the number of towers that will be lit up. So we can sort of picture it. Let's say the light is blue. That's gonna be lit up, and that one. So the 2 tall, the 5 tall, and the 6 tall will be lit up. And what we do is we're moving these around, so we know it for this one, then we put the last tower here, and we are given the number again, then we put the last number to the front and given this number again. So from here we can make a couple of observations. First, there's gonna be, so we're given the, again to, I need to stress what the problem actually is. We're given this power number for all cyclic shifts of the permutation, and that array is going to be called Ci. What do we know about Ci if it's correct? Because that's what we have to say in the problem whether there exists a permutation for which CI looks like what we're given. First of all, we know that there has to be a 1 in CI, because there's gonna be a point where the tallest tower, so this tower 6, will be the first one, and we know that at that moment we will only be able to see 6, so there has to be a 1, has to be 1, and we also know there's exactly 1 in CI. That's because for all the other shifts, tower 6 is gonna be somewhere not at the beginning, and there's gonna be a tower before it that's smaller than it, and we will see that. So there has to be exactly 1. Okay, this is the first observation. Another observation is that when we go through CI, we know that CI, and let's see, CI plus 1, in this transformation, it can either increase by 1 or increase by less than 1. So the difference between them, CI plus 1 minus CI, is smaller than or equal to 1. Why is that? Well, let's see, when it increases by 1, it's when I have a small tower at the end, let's say like this one, and it comes here to the beginning. When that small tower comes to the beginning, then we're gonna see this smaller tower and the one behind it, so it increases by 1. It cannot increase by more than 1 because the rest of the permutation will be left unchanged. So we know that it can be increased by at most 1. It can be decreased by a lot more than 1. It can be decreased arbitrarily. We can see that by some examples. Let's say we have like a medium-sized tower here that comes to the front. Well, it's gonna block all of these, and the power will be 2. And this condition also has to hold for the last and the first element of the array. So for this example, 3 to 1, it doesn't work because from 1 we increase it to 3, which is an increase of 2. So the answer for that is no. And what I found, that this condition isn't only necessary, but it's enough. So if this condition holds true, then then we can construct a permutation which will have a power sequence or a CI equivalent to the one that we're given. That's the part that I don't have conclusive proof for. I tried some of them, and I could construct one for all of them. I can also show code for this problem. Basically, I have my 2 conditions, so I check how many 1s there are, that's count 1. I count how many 1s there are in AI. I read it in as AI, not CI, because, I don't know, it's simpler. And then I check the neighboring elements, whether their difference is smaller than or equal to 1. And if there's 1, 1, and okay, so the difference is always smaller than or equal to 1, then I print yes. In problem D, we are given a range from L to R, and we also know that this range has been turned into an array AI by some process that is like sort of unknown to us. First of all, we put all the elements of this range into an array. Then the elements were put into an array. They were permuted in some order, and all of the elements were then XORed by X. So that's we did bitwise XOR of all of the elements. And we are given this final like contorted array, and we have to find which X was used for XORing all of the elements. And for D1, it turns out that the solution is pretty simple, because in D1 L will always be equal to 0. What we do is for all numbers from L to R, so from 0, 1, R, we calculate how many numbers have the first bit set, how many numbers have the second bit set, and etc. So we have this count I, which says how number of numbers with number of numbers with ith bit set. And then we're also gonna have a count 2 of I, and this is gonna be the number of numbers with ith bits set, but not in the original range, but in the contorted array, or the new array, the one that we're given, so in AI. And the way we get X is by going over the bits from 0 to 17. So J equals 0. Well, we actually don't need to go to 17, so 16 is enough. And if Cj does not equal C2 of J, then we know that the jth bit of X is set. Because if it's set, then it swapped the it swapped the bits. If it is equal, we can have a scenario where let's say let's write up the numbers from 0 to like 4 or 5. 0, 1, 2, 3, 4. So it's clear if the second bit of AI looks something like this, then clearly the second bit of X is set, because there are a different number of ones here, and we know that A is valid. It says it somewhere here. It is guaranteed that A can be generated using the steps. So we know that it must be that the second bit of X is set, and we swap these values. What can also happen is that let's say that for the sequence in AI, the first bits look something like this. Here they are different, but for all Cj and C2j, there are the same number of ones. There are the same number of set first bits in AI and in the original range from 0 to R. So that seems to be a problem, but what seems to happen is if we start from 0, Let's swap all of the first bits. So we have 1, 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1. What seems to happen is that all neighboring numbers, or all the numbers that were in here, will also be in the transformed version. So this is this, this is this. We can match these all up. Again, for this part I don't really have proof, I just noticed this and was happy. I thought that this would be always true actually, so I submitted for the second part, but this doesn't hold for D2. I can show a counterexample for D2. Let's have the numbers 1, 2, 3, 4. So that's 1, 0, 0, 1, 1, 0, 0, 0, 1. Here, if we have a new sequence that looks like this, 1, 0, 0, 1, we can map some of them, but these two will not have a pair in the original, so it doesn't work for D2. But for D1 it seemed to have got the correct solution. For this, the code is pretty simple. Oh wait, this is something different. We go iterate from L to R, read in all AI, and then go over the bits. So this is like n log n. Go over the bits, calculate C, J, and C2, and then if they are not equal, I'm just gonna set the jth bit in X and then print out X. Alright, so thanks for watching this video. I hope it helped. I'll be reading all of you guys' feedback, so please say anything that you think is notable, and I'm looking forward to seeing you guys in the next video. Bye!